so we can have a couple of beers. So this is the second part of today's talk, and thanks once again to Josue for the first part. So I thought that we have a bit more for today. I did a small presentation of Advent of Code. So who actually heard about Advent of Code? Have you tried it? Ah, Josue, you did. You're awesome. So Advent of Code is kind of an annual advent calendar with programming problems and puzzles. So if you want to challenge yourself, or you want to if you're interested in some puzzles, you can join this Advent of Code. So you can sign up for it on GitHub, and every day you will get another puzzle. And they usually start very simple on the first day, but they get more difficult as you go along. So I would say the first ones, they're quite easy to do. You can do them maybe in half an hour. But the later ones, you probably need a couple of hours, maybe even a day or an afternoon to solve them. And the idea is you can use any programming language you like. So there's no bias. Everyone gets a unique problem input. So you cannot just look at someone else's input and solution. So you get your own input, and you have to find your own answer to do that. And these puzzles become, as I said, more and more difficult. And there is a competitive element. So those people who really want to get into the competition, there's a speed contest. So as soon as the problems are released, it is the question, how quickly can someone find the answer? And the quickest people do this in 20 minutes or less sometimes. And these are already the very difficult problems. But I explain a bit more about this. And it's easy. You can sign up with GitHub. So usually I don't really have that much time for these kind of things, but I thought maybe I do a few of them, which seem interesting, just so I can, explain a bit more about it. And you can always learn something from these problems. So if you go a little bit beyond what is required in the problem, there's a lot of possibilities to learn stuff. So I can quickly maybe just show you how the website looks like. So this is a website. I think it's not very. Let me make this a bit larger. So you can sign up, and then you get this picture. And these stars on the right basically mean that you've done a problem. And you can then look also at the different problems. And each problem comes with a little sort of explanation. So this time there is this quest to find some chief historian who got lost in the North Pole. And there's always a cute little story that explains you some kind of background and wraps it up into a little problem. And then at the end, you have a challenge to solve. And there's usually two parts of a problem. So they explain what the problem is that you have to solve. And then there's two parts to it. There's the first part, which is usually a bit easier. And you have to give an answer to the problem, which is sometimes a number or a string or something. And there's a part two, which is usually a little bit more difficult. And especially if you go to later problems. So the idea is to have something which is for everyone. So if you are more sort of entry, junior, you can most of the time solve the easy one, but the second one requires a little bit more thinking and insight. So this is this annual competition. Have a couple of friends who do it, not all of them. So there's no need really to do all of the problems. You can just, do a few of them that you like. You can do the easy ones, difficult ones. But to do the last one, actually you need to solve all the ones before. Because each time you do a problem, you're getting some more of this kind of, and you need this as an input for the last problem. So you have to basically solve all the problems. And it's quite a commitment. I mean, there's people who are really serious about it, and they do this every day, every night in December. But you don't have to. I mean, it's not something that's compulsory. It's meant to be fun, I think, in some ways. So that is basically what the competition or what the puzzles are. As I said here, every time you solve a problem, you get a star. So you can get 2 stars per problem. The first star is like the easy one. The second one is the part 2 is usually a bit more difficult. Yeah, and to solve the last one, you need to solve all the ones before, which I'm not sure I will do because I have not so much time. But I mean, who knows? Maybe throughout the year, by the end of next year, maybe might be a chance. So these problems have different levels of skill in terms of their difficulty. The easy ones, I would say, you can do in an hour if you use a high-level language like Python or Java. More difficult ones take a bit more time. So the interesting thing is not just about coding, especially if you do the difficult problems. You really need to think about the solution. You need to do some sort of mathematical analysis, sometimes think about shortcuts, because usually the way these problems are phrased is that the first one might be easy. The second one, you cannot just do naively by brute force. You have to find some clever way to solve the problem using some optimization or using some kind of insights that allow you to get around this kind of brute force approach. So they expect a combination of clever analysis and coding. And if you have some good knowledge in algorithms, optimization, and mathematics, that's definitely an advantage. And the reason I'm showing this here, because this is an embedded group, is because this year they also had some problems which are particularly interesting for embedded systems for two reasons. And I will explain this more. So the day 17 problem was called Chronospatial Computer. That's just a fancy term for the story they have. So it's part of the background story. And there's another problem on the Christmas Day, crosswires. I'm not sure whoever would spend an hour or several hours on Christmas Day to solve that problem. But anyway, as I said, you don't have to do it. Maybe you can do it early in the morning when everyone's still sleeping. And these are also incidentally considered the more difficult ones this year. So I looked at some sites because there's lots of discussions on Reddit and so on. And these are the two which are considered more difficult. I will talk a bit about this one and maybe a little bit about that, depending how much time is. And let's see if we can solve them. So I want you also to have some ideas. And I don't want to give you the solution because that's boring. It's more like I want to try to lead you to how I would solve them. But there's always different solutions, so you can find your own solution in many ways. So let's have a description of the first one. And just to show you how this description looks like. So when you go to day 17, you're finding kind of this quite long explanation. And there's a bit of background stories again, so with these historians, and they find the strange device, so which is a CPU or computer. And then they're looking at some manuals and they find, oh, cool, we have a description of a 3-bit computer here. So this computer has 8 instructions, and all these instructions are kind of presented here. So we have a kind of very simple computer, which is a program counter. It has 3 registers, A, B, C, and that's all explained in the code. And then you have an instruction which can be one of these 8 that are explained here. So we have this one here, ADV, BXL, BSD, J and Z. And if you've ever done assembly programming, this seems maybe a little bit familiar. I mean, of course, this is a completely hypothetical language, and it's not used anywhere, really. But it's just to give you the feeling how it is to do assembly programming in some way. So each instruction has an operand. So the instruction is 3 bits, and then you have a 3-bit operand as well. And they're explaining in various ways how these operands are used. So for instance, if you look at this BXL instruction, so the BXL instruction, opcode 1, calculates the bitwise XOR of register B. So remember, you have 3 registers, and the instruction literal operand. So the operand is interpreted as a literal here. And then stores the result in register B. So this is very synonymous of the sort of 8-bit computers that you had in the 70s and 80s. So very simple machine model with a program counter, with a few logic instructions. So this ADV instruction, for instance, performs a division. It also stores the result of the division in a register. You have a jump instruction, only one. So very simple instruction. The jump instruction does nothing if the register is 0. So it just goes over. But if it's not 0, it goes back. So this is almost similar to how like the 6502 instruction set looked like. But it's meant to be simple. So it's not for you to write a whole interpreter of an assembly language, but just to get a feeling of how such a language looks like. The out instruction outputs a number. So the idea is you're running your program, and the program outputs a sequence of numbers. And you start it in some kind of initial state where the registers have certain numbers. So when you're reading through all of this stuff, you're kind of getting at the end a little problem. So there's some instructions here that tell you in detail how you execute a program. So this is very explicative. So it's very, very, very nicely written. So not to leave any doubts about what you have to do. But in the end, your input is going to be a program. So you're getting a program made of these kind of numbers, and you have to figure out how to execute it. And I just go back to my slides now. So we've kind of vaguely understood how this works, and my slides must be here. So I'm playing the slideshow now again. And this is just a summary of how this very simple machine works. So you have a hypothetical CPU with 3 registers, A, B, C, that can hold integers. That means they're not bounded. They can be infinitely, long, large numbers. 3-bit opcodes, 8 instructions, and each instruction can have an operand. And what I didn't explain is an operand can be just a literal number or what they call a combo operand. So it can have 2 bits, and it also can refer 2 bits literal, or it can refer to register. So you can also, some instructions that take a register as an operand, which is also very, very common. These are the instructions here. The names kind of sometimes tell you what the instruction is doing. So this means it's a division. You have an XOR here. I kind of forgot what this one's doing. But you can look all of this stuff up. This is a jump instruction. You have another division instruction there. And this must be a typo because I think I've copied the wrong one. Yeah, maybe, yeah. It's non-deterministic. Yeah? Go on.
Could you explain a little bit more about the combo thing?
Yeah, we can have a quick look. So the combo operation, let's go back to here, is explained here. So you remember you have a 3-bit instruction, a 3-bit memory. And you can have values from 0 to 7 with 3 bits, no? So if the operand is from 0 to 3, then you just think it as a literal value. But if the operand is a 4, then you assume that it refers to register A. If it's a 5, then register B. And if it's a 6, then register C. And 7 is not actually used. And this is actually quite common. When you look at real CPUs, there's a lot of instructions which are not used, which are kind of supposed not to be used, but people then figured out how to use them anyway because they do something useful. And that is how you find all this amazing effects in games, because I figured, oh yes, I can have an instruction that does 5 things at once. And nowhere it is documented. But so the combo operands allow you to refer to the registers because some of these operands have targets. So here says the value of a combo operand can be found as, no, this is not what I meant, but some of these, let's have a look. Some of these actually use combo operands. So the BST instruction calculates the value of its combo operand, modulo 8, just keeping the low 3 bits. So modulo 8 is just you're cutting everything off except 3 bits, then writes that value to register B. So you can here decide where you're taking the value from. So this kind of compositional way to write instruction is actually very common in instruction architectures because it kind of reflects the orthogonality of instruction set. And we had this talk about RISC-V, I think we also talked about this, how the instruction set is mapped and so on. So this is actually quite realistic in some ways, but much, much simpler to what you have when you're doing real stuff. Yeah?
So like for that, if you did like BST4, that would take the value from A and store it into B?
Yeah, let's have a look. So I think you're right, 4 would be A, no? So I need to go a little bit back. So 4, yes, that would be A. So it would take the value from A, and then it would apply the operation that is specified. So it would use modulo 8, this operation, and it would put it into B. So if A has a value, I don't know, of 15, it would put 7.
Oh, okay. The value it finds, it doesn't. Okay.
So one thing to notice is that the registers can hold any value. So it's only the instruction set is 3 bits. The actually data width of the machine is infinite. Well, at least theoretically. I don't think, I mean, I didn't find they talk about integers, but integers have dual meanings. Mathematical integers are actually infinite. But computer science integers are 32 bits. So there's always like a clash of cultures. And cryptographers is just 1 bit. So well, no, actually not. But so this is basically, we could go through all of these instructions to see what they do. And I will explain maybe a bit later because we need to look at this code at some point. Not yet, but there will be a part 2 of this exercise where you cannot avoid just ignore the code. Because so far, this is all just a matter of reading the specification and writing the code, which is very much what we do as software engineers, right? So it's not kind of unfamiliar. So let's go back to the slides here. Cool. So the problem for part 1 of this exercise is, so assume you have your architecture here, and you're given a program which looks just a sequence of numbers, and you have some initial values in your registers. So this is when the machine starts. What is the output? And remember, there's an output instruction as well. So if I go back to this one here, we have this instruction out here. So this instruction here outputs a value. So instruction calculates a value of its combo operand modulo 8 and then outputs that value. So the program is going to output a sequence of values whenever it hits whenever it sees this out instruction. So the problem again is then, cool. So we have this program here, which is your puzzle input. So apparently maybe everyone gets a different program. I don't know. But in this case, this is your register, this is a program, what's the output? So this is a fairly straightforward problem, I would say, for computer science engineers, software engineers. Let me just put this large again. It is something that you sometimes do in embedded. So when you design, I mean, has anyone designed their own CPU at some point or played around with that kind of thing? Well, that's not so common, but it's possible. I mean, there's like a small community of people who like to build their own CPUs. And when you Google this, you find like a lot of kind of small designs of CPUs. So it's not an uncommon task to do that. I just talked, was it about the Pico? Yeah, and the Pico has also a mini CPU for state machines for reading signals. So it has this mini language to write programs to process signals, very low latency signals. And yeah, you find these kind of little languages everywhere. So to write an interpreter, you can take advantage of object-oriented design principles, of course. You can get crazy with objects and classes. And if you do it well, you can also perform some validation, so of debugging your code, running your code. And these are just a few examples. So the J1 is one which I looked at some point. So I wrote an interpreter for that as well as part of a little cross-compiler, host compiler. The Amiga had a coprocessor Copper, which only had 3 instructions, but it was really useful. So whenever you play a game with parallax scrolling, it's because the Copper was kind of feeding the hardware registers in the right time to change the colors of the background and the resolution and things like that. So, and yeah, the POC is another example. So it's not an uncommon task. So let's have a quick look at the code. I don't want to maybe look too much at it, but just to say how you might design something like that. I hope this is readable, or should I make it a bit bigger?
Yeah,
I can maybe make it a bit bigger. So I just need to go to settings. Maybe let's try 28. Maybe that's big enough now, hopefully. But now I also need to make the window a bit bigger so we can see that. I mean, readable? Pardon? Ah, yes. So this is a program actually. So I hard coded this. I could have cheated. I cheated a bit instead of loading it from a file. But basically, these kind of numbers is an encoding of the actual program. And this is just the example that was used in the description. So the description had a small example. Anyway, so we have an abstraction of a machine here. And the way I implemented it, and again, this is just an example. You might implement it in different ways. I haven't thought too much about it. But for one, I'm encoding the registers as part of this machine class. So there's an abstraction of a machine. And I'm using long, knowing that I don't need more than long. I mean, we could have used something bigger, but long seems to be working. So the machine doesn't have a lot. It has 3 registers. It has an instruction pointer, which increments every time you run an instruction, except you're doing a jump. Then it changes. And you have a flag that tells you if you halt it. So there's this, when you reach, I think there's a special condition when you reach an instruction outside your memory or something like this, you will just halt the machine. So basically that means that you sort of stopped execution. You have an array of memory items. So the way that this machine manages memory is basically by means of an array. It's a data structure, and these memory items are already decoded instructions, so they're not just numbers. And you have a list of outputs. So whenever you create an output, you are putting it into this list so that you have some way later to see what the output is. So when you create an instance of this machine, you need to give it a program. And the program is just a sequence of numbers that we've kind of seen here. So this would be your program. It's just an array of numbers. But you need to kind of populate this memory structure with the right sort of objects. And these objects already have the intelligence to execute your program. So the idea of this design is that you're putting elements, memory items, into this memory, which already know how to execute instructions based on the encoding of this kind of machine here, where you have the internal state, the state of the machine. So the first thing that happens is you're going through this program array of integers. And one thing about this architecture is that it's a very homogeneous. So every even instruction in memory is an instruction. Every odd place in memory is an operand. So you always have 2 elements in your memory. You have an instruction and an operand. So which means you can just step through your memory until you reach the end and take the ith element, which is your instruction, and the ith plus 1 is your operand. And these, by the way, do you use asserts? Are you a fan of asserts or not quite sure what they do, or you don't like them? So I use asserts all the time, because asserts is just a way that helps you validating and testing your code when you write it. When I write a test case, I have to write the test case. But an assert statement sometimes captures an assumption that I'm making in the code. For instance, here I'm assuming that this instruction here that I'm reading from the memory is 3-bit. I find about 80 to 90% of faults in my code through asserts. And I also test the code, but this is a very effective way sometimes of testing your code, because what an assert does, it checks some condition, and if it's wrong, it doesn't continue, it just stops your program, set assertion failure. So it's a way where you validate, this is why I understand this problem should be doing, and this is what the program actually does. So it's a very powerful technique to testing more than you test. So you always get these kind of asserts for free. You only have to write them once, and whenever you run your program, they're executed. And that makes them quite useful. So asserts are a good thing. And don't use printf. Printfs are bad. Asserts are good. And if you really want to print something out, use a logging framework or something like that. So that is what we always tell also our clients and our customers to say, well, this is, there's a certain practice behind all of this stuff in a certain universe. So,
Quick question.
yeah.
So right now that you're talking about the server, why you are making an assertion about the length of the program being even? Okay.
Well, because I have no control over the input. And I might have a routine that loads that input, which is faulty. So, of course, I can have just a look at this and say, well, this is all in the right range. But it's part out of the control of my program. So it captures an assumptions I'm making by the function. And program is all about assumption and commitment. If I write a function, a constructor, anything, it makes assumptions about the data it gets. When it finishes executing, it makes a commitment what it has achieved. So when two functions are calling each other, one function guarantees to the function that it calls that it fulfills something called a precondition. And a precondition is what this method assumes is true when it's called. And as a programmer, you never write this stuff down. It's just in your head. But someone else might call this function and not guarantee that precondition. And then you have a problem because there's a mismatch between what I am assuming writing this code and someone else is guaranteeing who calls or uses this code. And you find these kind of mistakes through assertions because assertion says, well, I'm assuming this, but you haven't guaranteed it. So whose fault it is? Are my assumptions too strong? Or are your understanding of this function different? And this is how you're finding this kind of mismatch between the two.
This assumption of the kernel of the length being even is from your intuition and the kind of way you see the problem? Or because, for example, the 3B
Well, it comes from the,
instruction is because of the problem statement, right?
Yeah, it comes from the exactly. It comes from the problem statement.
Okay.
So usually these assumptions originate from some kind of requirement specification, and more often it is not clear what the assumptions are. And this is where software engineering meets systems engineering meets requirements engineering and all of that. So if I write the code, there are actually languages where I can make this much more precise than here. I can actually make this part of the specification of a method. But 95%, 99%, maybe this is not used in real engineering. And the asserts is really just a kind of way around it, making things a little bit better.
Yeah.
Not perfect, but just a little bit better. And I really guarantee you that you will find faults. Even if you have an obvious assertion somewhere, it will sometime allow you to find a fault, because they always run and they always help you to validate this. But anyway, so I didn't want to go too deep in this, but I want to quickly show you how this model actually looks like. So when you reset the machine, you're initializing all your state to various data. So you want your registers are passed as arguments, instruction pointer starts at 0, and your machine is not halted yet, so it's just starting to work. And you're clearing your output. So this is just a list which you empty. When you encounter an error, this thing just bails out. So I thought it was nice to have a function like that. And the decode functions here, again, are based on the specification that you find in the problem. So it's there's a very strong relationship between the decoding here of an instruction as an opcode and generating these objects here. And as I said, I'm using objects just to have a nice way of capturing the behavior of operations. So by having classes there, you can have a nice little design underneath that makes it very easy to execute programs. And we need a decoding of instructions, and we also need decoding of operands. And again, I'm reflecting the specification here. So I want to have a design which is close to this explanation. So I have a combo operand and a literal operand. And we will see later how we take advantage of this. There's also one instruction 4, which is this BXC, which doesn't use the operand. So there's also something called an ignored operand there. Now it gets into the kind of nice object-oriented little bit. So let's just ignore the stuff for now and see how the instructions look like. So an instruction just has, it's an abstract class. So it's not an instruction, a memory item is an abstract class. And you have to implement it. And what you implement here is these two functions. So you can either execute if it's an instruction, or you can get the value if it's an operand. So if a memory item is an instruction, you can execute it. If a memory item is an operand, you can get its value. You shouldn't try to execute something which is an operand, and you shouldn't try to get the value of something that's an instruction. So that's some tests that you can run in your program. So I have an abstract class of instructions which already cause an error, throw an error if you try to get its value there as an operand. And we can then implement, let me just see what this was. So an instruction has another function where you can get the operand of an instruction, which just goes one beyond the current instruction pointer. So you cannot call this getOpValue, but you can call the getOperand of an instruction, which makes the later code a bit easier to write. And just forget about toString. This is just for dumping the program, which I will show later. So how do the instruction look like? Well, we have to implement execute. So this is a nice thing about using an interface, because by the fact that we use this interface now, all we need to do is for instruction implement this execute. And every instruction of the machine that we previously saw will have a function to execute it. And in this case, this function basically tells if the machine is still running, so it hasn't halted. There's a few assertions more here. For instance, I want to know that the instruction pointer is valid. I want to know that the operand is in the right range. So as you can see, I'm using a lot of assertions in my code. And that helps me also sometimes to find stupid mistakes that I don't see. So this one takes a first operand, which it gets from register A. It takes a second operand, which it gets from the operand of the instruction. And because we are calling this operand function here, we make it very easy to decode the operand value. So the nice thing here is we don't even have to worry if this is a combo operand or literal operand. We can just call this operand function and leave it to the class that implements the operand to tell us what the operand is, because this will result in a call of getOpValue of the next memory location. And if the address is not valid, then we halt it. And this just returns in the end if we halt it. And we're doing this for all the operands. So as you can see, most of these operands, and I should talk about this because the instruction pointer needs to increase. And this is a model of the memory, basically, that model of the machine that we have. Every time you execute an instruction, the instruction pointer increases. And we do this for all the instruction. And it's just a few lines of code. If you write a real emulator for a real CPU, it will be a lot more code. But not necessarily, because in the end, the individual operations usually there's not a lot to them. They're changing sometimes your registers, they're changing the flex of your CPU, sometimes they change the address. And in this way, when you play retro games and they emulate like some old retro hardware, this is like something similar underneath. And you find this everywhere. So it's quite easy actually to write an interpreter. So this problem is to give a little bit of an idea how to do it in the small on an example which wouldn't take you, a month to write, but you can maybe do it in an afternoon or less even. So we're having all these instructions here defined, and we also need to define operands. So we have the same interface here. The only difference is that the execute function cannot be called because we cannot execute an operand. But then depending on what kind of operand we have, we can then, implement this getOpValue in different ways. So for instance, for literal operand, the operand will just record a literal value, which it gets when it's constructed. For a combo operand, we have to again look at the value. So if the value is 1, 2, 3, 4, we're just returning that particular value. So this is again like in literal. But if it's 4, 5, 6, we're looking at the machine registers. So by using this kind of design, you can make your life very nice and easy. And once you've implemented all the surrounding framework in terms of objects, we also have a toString function. And we need this later because we want to see how the program looks like. In the end, you can execute the program very easily. So the function that executes the program is basically, so we have this execute next function here first, which looks at the machine. If it's not halted, it will just execute the next instruction and then tell you if the machine is halted. And all we need to do now, if I can find the right function that calls that function, is, I think maybe it's on the bottom, I'm not quite sure. I haven't looked at this code in a while, I don't quite know. Yeah, execute program. It just executes the next instruction until we halt. So it's actually, none of these functions is really big. There's a lot of small functions there that execute this. So let's see if that kind of works. So I'm having, I hope this is, I'm having a make file, so I can just run 17 and run this. And so this actually tells me, first of all, the program, what it looks like. Let me make this a bit bigger, because I think this is still a bit small on the big screen. But you kind of see, first of all, what the program is. And this is cool already, because we didn't see that. It was just numbers. But now we can actually see what the program looks like, because I had a two-string function that tells me that. And then this is the output the program produces. And this is, of course, based on the inputs and the initial state of the machine. And when you participate in the advent of code, at some point you have a possibility to submit your answer. And I've already done this. So this is the output. And when you submit this, this is how you get a star then. So you have to go through all this stuff to write that code. This time it's written in Java. You could have used something else there, maybe something more embedded. And then in the end, you're getting this output. I mean, the reason I use Java is just because it's easier to explain it. I think if I start to do it in Verilog or VHDL or Chisel, I think I could still do it, but it would be more concise, but it would not necessarily be easier to see. So we get a bit of an idea what the program is. We've done it. Now, we've done the first part, but now it gets really tricky. And let's have a look what the second part is, because that is where it gets more interesting. This is not super interesting, I think, for anyone who knows a bit about programming, object-oriented implementation, and maybe a little bit about hardware. This is not particularly challenging. It's fun, but not so challenging. So this is part 2. So now consider a program which outputs a copy of itself. So we have a program which has a certain data, and when we run it, we want to produce exactly the same data that the program.
Oh, so now we are writing works.
Yeah, in some ways, yes. It's and it's a kind of reminiscent of the proof of the halting problem, where you have a program which you feed its own Gödel number. So there's a kind of referential issue there. But so we want to know the smallest initial value of the register A. So remember that when you start this little program, the registers will have particular values. And A will have a non-zero value, and B and C will be 0. So depending on the value of A, you get different outputs. And now we want to find a value of A that just outputs the program itself, basically. So this is a different problem. And one thing I can tell you is that this value is greater than 100 trillions. So just by trying values and then seeing what they output, you're not going to get to the end of the problem. Most likely not, unless you write it very efficiently. But I think 100 trillion is beyond what you can do with brute force. So how are you going to do that? I mean, you understand the machine, how it works. How would you solve the problem? I mean, so this is a part where the programming doesn't always help you. So we know what the program looks like. So we know what the program is. But maybe it will help to actually understand what the program does. So this is a part where you might want to get a better idea what the program actually does. And maybe you can find a more efficient way than testing all possible values for A. I mean, if I would test all possible values for A to maybe 1,000 trillions, I'll probably find the right value that does that. But difficult to do that. So here is a program again, which I showed you. And this output is easily generated from the toString function of instructions. So when you have a nice design, you can just, easily go through your memory array that I construct here. So if you remember, we had this model of the machine where you have a memory here, and all these memory items of a toString function, you can easily generate the output for that. So let's go back to the slides and make this a bit bigger. Cool. So you need to look each of these instructions, what they do, and they have an instruction operand, instruction operand, instruction operand, instruction operand, and so on. And it's a little bit tricky to see what happens here, so I translate this into Java code, like pseudo Java code. No, this is not even pseudo Java code, this is actual Java code. So you have an equivalent program in Java to the machine, but it doesn't have, it does all of these operations. It doesn't worry about the instruction pointer, just every time you're changing the value of the register when you execute an instruction. And in the end, you have this out here, and this is what this does. Now, when you look at this program, this is not all of it. You have a loop here which goes around. So really, this is something which gets executed in the loop. But the loop continues as long as this operand A is not equal to 0. So you have this jumping here, op0, which jumps all the way back to the start here. So this will just continue going through until A becomes 0, essentially. So now this still is a bit confusing. So how do we can make more sense of this? So the next thing I did was just to just make it a little bit easier to read. So this is basically the same as here, but I'm kind of doing some simplifications and substituting stuff a little and doing some simplifications of the Boolean logic to get at an equivalent program, which is this one. Now, you just have to take my word that these are equivalent. We could prove that. There's some techniques we can actually prove these two are equivalent if you really wanted to do that. But I think right now here it becomes a little bit easier to see what's actually going on. So in each of these iterations, B is just 3 bits. So we're taking the modulus of 8. Then we're calculating C by taking the value of A and we're shifting it to the right. So now we have a shifted value in C of the value of A. So B and C kind of picking some stuff from A. And then we calculate the XOR of B and C and 6. And this is basically our output. So we're truncating the 3 bits from B as the output. And if you want to visualize this a bit more, you can kind of think if these are the first 10 bits of A. Then you've got 10 bits here, then you're shifting that. So here the maximum you shifted is here. And then you XOR it with another value. And this is how you get the next result. Now, the interesting bit here is that the result only depends on 10 bits. So you don't need to look beyond 10 bits to know what the result for the next digit is. And this gives a little bit of a solution that we could adopt. So, of course, this is just for one iteration, and we need to execute many iterations because every iteration should, this B here should give us basically the output that we're expecting for the program. So every time we're running through this loop, we want to get another bit of that program, another digit of that program. So what we're going to do is we start from the end rather than from the beginning. So we're building this value A incrementally. So we're starting from 0, and then we're thinking, well, the last value we want to output is the end of the program. And we need to find the first 10 digits to do that, kind of. Well, in fact, we don't have to go through all the 10. We can even go through less, but that's a different thing. So but this is a much smaller search space. Like 10 bits is not so much. It's like 1,000 possibilities. And then we can get the first output, the last output of the program. And maybe we can kind of work our way backwards. And every time, we can add something to this A. So the thing is, the A gets shifted 3 bits every time. So basically, this is actually a particular sort of algorithm. It's synonymous of XOR shift random generator, something like that. But what we want to do, instead of going through all the possible values of A, we want to incrementally construct them. Every time, 3 bits. Shifting, find another 3 bits. Shifting, find another 3 bits. And when we understand how this program works, it takes a little bit of mental effort to conceptualize this. But seeing that we only care about 10 bits, this is actually possible. So there's a kind of, how can I say, dependency, which is limited in terms of the output. It's not that every number that we're seeing depends on the whole A. No, they only look at the window of A. And this window shifts all the time. So that gives us some hope of a greedy algorithm to solve that. So this is basically how the algorithm works like. So as I said, it starts from the end. And we have this function that calculates the lowest A. And we're passing it the current value of A. So we're kind of, and I need to remind myself exactly now how this algorithm actually works. So depending on the value of A, so initially, the value of A is 0. So this is how many different values we're going to try. I'm not sure why I'm only trying 255. I thought it was 1024. But anyway, it seems to work. And the first time, we have more to try. But afterwards, we only have to try 3 bits. Because as I said, every time we're shifting 3 bits to the right, and then we are taking the next value of x, which is inside this kind of small window. So we're doing an incremental construction here. And we simulate, we're calling the simulate function with the next value of A. And we're checking if this is equal in terms of the output to the program. And the index starts from the end. That's maybe what I should say. The index will be the last element of the program, which kind of exemplifies this reverse construction. So we're starting with the last output that we want to construct, and we're making the value A bigger and bigger. And just to show you, this function actually, every time we call it, it returns the next value that we see as an output. So this return here kind of matches the output here at that point. So we're starting with the largest index, and we work our way backwards. And you see that by index always getting smaller, until we reach index -1, and then we have it. So there's a little bit of backtracking here involved that we need to do. So because we might make the wrong choice, and there might be more than one choice. And there's no guarantee that actually we get a result. So we need to, as I said, go through all the different values here. And whenever we find one that works, we're having a recursive call, and we're trying to get further. So this is a kind of recursive way to construct this value. And if there is a solution at some point, then we will return it here. So, and this is basically here where the base case resides. So if we go from our index all the way to the start, from the end to the start, so index becomes -1, then we get the base case. So if we want to run this program, that is basically the output we are getting. And these stars kind of say how many times we have to do backtracking. So from these trillion of possibilities that we need to explore, if I run this now, this runs very quick. And this is because we managed to reduce the space of possibilities that we need to explore. Rather than going through all the possible inputs, we have kind of just cleverly figured out what this value of A is. And we could actually even modify the code a bit and see how it gets incrementally constructed. So I could maybe just put a print somewhere here, and the actual code that does this construction is here. So every time we are recursing, I'm going to try and print this. And what we can see here is basically how this value gets constructed. We're starting with smaller values that get bigger and bigger, and every time we're adding 3 bits to it. And in the end, we also need to validate that the result we're having, which is this result here, yes, that's the right result, actually produces this kind of output. So to go back to the slides, that's part 2, and that's solved. And this kind of gives a bit of an idea how these problems are, especially the more difficult ones. Now, there's some people who manage to solve this in 20 minutes. I don't know how. So I'm absolutely amazed that you can do that in 20 minutes. But it's very weird. But I think the reason is maybe that they already have some code in place which they can just put together. And you need to have some suspicion how these problems work. For instance, this algorithm that we use has a particular name. It's called greedy. So there's a class of algorithms which are greedy, which means that it's not a problem where you have to go through exponentially all possibilities. You can just bit by bit construct an answer. And so in this case, this is what we are doing here, is to have a good guess that this works. Of course, we had to look at the code, but some people might have a guess which goes, they don't have to look at the code. They just think, maybe I can do it like this, and they just try and apply that technique. So this is how you solve this quickly. I think it's more gratifying in some ways to actually understand what's really going on. But I think if you do this competitively and you want to do this in half an hour, you wouldn't have time for that. It's just, would take you an hour just to figure out what this code does and then do the next. So this was the first problem. The other problem, and I don't have too much time, so I just want to skim through it, and maybe also not depriving you from trying it yourself. The other problem is this cross wires. And let me show you the description of that one, which is the Christmas problem. So this problem gives you essentially a description of a circuit. And the way this circuit is described is that you have these sort of expressions here. So you have X or Y, which are inputs, and you have an output, which can be Z. So here, you're connecting an output to some inputs, an output to some inputs. So think of it as a Boolean circuit, basically. Now, in this simple example, we only have 6 inputs and 3 outputs. But the actual problem consists of a very long list of inputs and outputs. And each equation that you have here corresponds to some logical operation, which can be OR, it can be exclusive OR, it could be AND, and so on. And you have some variables, which are temporary variables. So you should think about this not as a sequence of equations, but as an actual circuit that blocks that you're connecting. And the problem of this is essentially that you want to know what the circuit does. So you're getting all of these descriptions here, and the actual problem input is actually bigger. So you have about 400 of these little, let's call it like assignments or equations. And based on these 400 equations, you need to work out for a given input and output, so you can interpret this as a number. So for instance, this will be 1, 2, 3, 4, 5 bits. And this could be a 5-bit number. You want to figure out what the result of this circuit is, So these random-looking names are just internal wires, and the ones with a Z are the actual outputs of the circuit. So the challenge is, again, that you're reading this information in, and you need to simulate a circuit. So we're going a bit lower from simulating a CPU, going to simulate a circuit. So they're kind of tricking you into being almost, at the electronics level. And this is actually how, logic works at the bottom level. Everything is made of simple logical constructs. So let me go back to the talk. So just to summarize, so as I said, the puzzle is in essence a Boolean circuit. The circuit has inputs and outputs and internal wires. you can interpret these input signals, which are Boolean. They're 0 or 1 as numbers. So because you have a lot of them, so they form some large Boolean number. And you have 3 kinds of gate, AND, OR, and XOR. And the problem is now, given 2 input vectors, x and y, what is the output if you're running that circuit? So what you need to have to do for the first part of this problem, when you're giving these inputs, is to implement the computation of a Boolean function. And I don't want to go through all the code again, because maybe we don't have enough time, and I want to show you the more difficult bit rather than this. So you can maybe have some fun to do that. We can model, of course, all the different elements of a circuit as classes. And we can model the bias as strings if we want. And the important thing is that we need some way to connect these gate objects, to say when the input changes, they compute their result and then they notify the successor gates of their output. So we can, this is not so difficult to have a little design behind it, where each gate knows its inputs, it knows its outputs, it is a function computed, and then it can notify the successor. There's one important assumption, which means there's no algebraic loops. So algebraic loops is if you're feeding back a signal in a loop without a delay. So there's a very simple way to create a very fast clock. You can take an inverter and just feed it back its input, or maybe a NAND gate works as well. And this, I think there's a special name for it. It's called hammer or something, particular kind of. So we don't have that, because such a circuit is not stable. You don't know what it does in a particular, it's not synchronous. It's undefined when you're reading such a gate. So we assume that this is not the case. And this makes things a little bit easier later. So I've implemented this, and I can quickly just run the code just to show how this works. So we have this 24. And this is basically executing the circuit for the input. And the input looks like this. So I have the inputs here somewhere. This is a day 24. As you can see, there's a lot of input signals, and then you have a lot of wires. And this basically, what you see here, is the output of all the Z wires, interpreted as a binary number. Now, where it gets interesting is actually part 2. And part 2, let me just magnify this. Part 2 looks like that. So part 1 you can solve with a little bit of trickery, programming only. A little bit of thinking, but mostly programming. Part 2, now we know what the circuit does. So it tells us the circuit is a binary addition. It performs a binary addition of 2 numbers. But the problem is that accidentally 4 pairs of outputs of gates are swapped. So the outputs of 4 gates in this circuit are just commuted. And that means the circuit doesn't work. So the question is now, can you find which of the wires are swapped? Just by thinking about, analyzing the circuit, the problem. And just to let you know, brute force, if you think you can do this with brute force, you have 222 wires. And if you want to pick 8 out of these 222 that you want to swap, this is a number of possible cross-wirings that you can get. Now, I didn't even consider the fact that you need to match them as well against each other. So again, with brute force is a bit, and this is where your embedded systems knowledge comes in. So we need to know something about adding numbers. So how are numbers added typically in an embedded system, like in a CPU or in some microcontroller? How does it work? So we have usually a circuit that can add at least 2 bits. There's only 2 bits. So it's the smallest possible adder that you can have. So you have 2 inputs, AB, you have an output. And also you have something called a carry input. So when you do addition on a piece of paper, what you learn in school is always you do an addition and then you have some overhead and you have to carry that over, some carry over to the next digit. And then you have another column where you put all the carries. So you somehow need to know the carry, and you also might generate a carry out. So an adder, it's not always implemented like this, but the simplest way to implement an adder is in terms of having a lot of these small components, and you chain them together. By the way, why is that not so good in a real system? Or what's the problem? What could be the problem with that?
With changing
Yeah?
the delays.
The delays, exactly. So David just said it. So when you can kind of see when you chain all of this, that this longest signal path goes all the way from the initial C in to the final C out. So the time this executes, the more bits you have, linearly increases the time. But we don't care about this. I mean, there's other designs, but this is the one they actually use. So assume that this is a circuit we have. So this already gives us some ideas how this can be solved, because the question is now, are all cross wires confined to just one adder? So someone might just think, oh, maybe I change this output with this output or something like that. And if that is the case, it reduces the problem, because we don't have to look anymore at the whole circuit. We can just try to figure out all these adders. So if you have some clever way to look at the circuit and just figure out which gates belong to which adder, maybe there's a nice way to solve the problem. And this is the combination of assumptions, because on the one hand, we don't know what the circuit looks like, but we can assume it looks somehow like that. So I've kind of looked a little bit, reverse engineered so one of these adders, and then found out it actually looks like that. So that's exactly more or less, maybe not exactly, but it's similar to that kind of design. I think it's made of 5 gates. And all we need to do now in the program is to kind of write some clever code that actually tells us these are possibly the gates of a circuit, and see if that is enough to solve the problem. So we've now reduced the problem as a solution square to determine these sub-circuits for all these different adder stages. There are 44 bits, so there's 44 stages. And they all look the same. The only ones which look different is the first and the last one. The first one has a carry input of 0, so it doesn't need the carry input. The last one doesn't need to produce a carry input. In fact, the last 2 stages are condensed into one, because the last output is basically the carry output of the last stage. So the last bit that you output is the carry of the last stage. So we need some intelligent testing function to see which actually is the faulty. Is there, did we resolve a fault, or when we're changing wires? And that is, in fact, all we need. And it substantially reduces the space, because we only have to now look at the individual circuits. And this was quite similar to the previous problem, where we also reduce the search space. So a lot of these problems are based on this idea, how can you cleverly reduce the search space? And I just show you the solution. So without going into the code does some clever testing, and it tests each adder individually, each bit individually. And since this circuit is made of AND and OR gates and XOR gates, there's a kind of linearity property, which means if you leave everything 0, you're always going to get 0. So it has, and we can use that by identifying which adders are actually the faulty ones. And this is what we expect. There's 4 faulty adders. And this kind of supports our initial hypothesis that the cross-wiring doesn't happen between 2 of these, but inside one of the adders. And that makes the problem simpler. So we can solve this simpler. So all we need to know is to find a clever way to find the gates and the wires of an adder. And in the code, I have a function which computes something called a footprint. As you can see, this is a bit more code. But I have some functions here, for instance, which compute the footprint of a circuit. So it's this print IO footprints. And this enables me somehow to figure out which are the inputs and outputs of particular adders. So I have to embarrass myself that I haven't looked at this code in a while, but I just want to get the general idea across that the key, yeah.
That means do you need to codify each possible error and then to know what the output is to figure out what the swapping inside the circuit is?
This is another approach which I also used as an alternative, but there wouldn't be time to explain that one. This is more of a black box approach you're talking about to see what information can you get from the actual behavior of the system and then draw conclusions back, so it's more abductive to what the fault is. This is a bit more crude. So here you just want to reduce the amount of possible things that you have to swap. So, but this is an interesting approach. So I think if you think a bit more about the problem, I think you can exactly arrive what you say is you can look at possible ways I can swap the outputs and then based on that maybe arrive at this kind of conclusions. And you might get quicker to the actual aim. This is a more crude in some ways. So here I'm computing this footprint of a circuit, which is a set of gates, and I'm basically just following the signals. So I have some gate, some output, and I'm including the gates from the output, so like the front. So it's a propagation front of some inputs. And you can do this to a certain depth. In this example, you need exactly depth, I think 3 or 2, because they are very small, the subcircuits. So if you have the right numbers and you find the right depth, you have a really good chance to figure out which are the gates. And once you have that, you're almost done, because all you need to know is to find out the wires and then try to swap them and see if your testing works. You still need to write a testing function, though. So there's a bit more logic here, and this is basically the function that tests your adders. And it's essentially a loop where you kind of testing all possible inputs in 1, in 2, Cn. But as I said, you don't have to execute this so many times. Once for each stage. So it's not a huge amount of tests that you basically have to execute.
So it hopefully is not cubic. It hopefully is not cubic.
But if event is a constant, it doesn't matter.
Ah, yes. Yeah, yeah. Yes. So in the end, the code figured out which ones you have to swap, and you have to submit these ones as your answer. So just because we're running a bit late, I think we only have 5 minutes, and I don't want to make the generous Hacker Garage hosts angry. So let me just conclude this. As I said, everything I say on the slide I've just explained, so we don't need to look more at this. The key thing here to solve this is about assumptions. So it's a combination of things that you know as an embedded systems engineer together with some kind of meaningful assumptions you might make, some good guesses, and like a creative way to explore the search space. And that makes this problem kind of fun. And a lot of people found the faulty gates, but they didn't manage to actually write a code that fixes that. So there's also a bit of programming here that you need to write. So this was probably the most difficult this year, or at least in the most 5 difficult this year, because people really struggle with the search space. And maybe because they're not from the embedded side, they don't know how an adder actually works. And this definitely helps to have a wide knowledge of all these things to solve these problems. So conclusion. So this advent of code, I've never done it before, and even this year I've just looked at a few problems, but it's a very fun, challenging thing. And it's doable. So the part 1, junior software engineer should be able to do it. Part 2, I think you maybe need have more of a background in computer science, and they take more time, but I think you can work your way into the problems as well. And the problems are very versatile. So I showed you just 2. But there's other problems where you need to apply dynamic programming, shortest path, maze solving algorithms, linear algebra, hashing, memorization. So there's a lot of other interesting problems to do. And I use this to some extent just to catch up with the OpenJDK. So I haven't done Java programming probably in quite a while. I usually don't program in my work. So sometimes I'm happy to do a bit of programming just for fun. So you can have a look at these 2 if you want. You can try them yourself. And if you don't want to try them because you know seen some of the solutions, you can also try the other ones. And this is the link of the group. So if you're not a member of the Bots Up group, then just take this link. So I don't know, there's probably not too much time. If you have 1 or 2 questions, maybe then I can answer them. Yeah?
Can you please go back to the QR code?
Okay.
So one question.
Yeah?
So the first problem
Yeah.
And you did some kind of backpropagation on the final zero condition, right?
Yeah.
To kind of get the 3 bits.
Get the 3 bits bit exactly. So bit by.
But that would only work for the minimal value needed for A to reproduce the computer program, right? Itself. That was the challenge, right? Find the raised value of A such that it could reproduce itself. So, but the solution would only work for the minimal value of A because of the propagation.
Well, you could collect all possibilities. So I'm interrupting the search once I have a solution. But there's nothing that stops you from collecting all solutions.
Yeah, that was going to be my question. Like,
Yeah.
what would you do to try to maybe improve or further searching another A values?
Well, if you look at this code, it's a recursive function. And once you reaching the base case, you just return the value. So this might even be tail recursive. Yeah, it might even be tail recursive. But instead of having this one here, what you want to have is some kind of accumulator. So you want to have maybe a list of long and call this ACC. So this will be your accumulator. And instead of doing a return here, or before you do a return, you just say ACC.add. And you want to add.
You add that solution, right?
Yeah.
Solutions?
Yeah, to your solutions. This is not quite correct because it will just collect all the values of A, which you don't want after each recursion. But what you can do is you can keep another variable that gives you the current sequence. So you need 2 more parameters. One parameter that gives you the current sequence and one that stores all the solutions. So this is just a different way of solving a recursive problem. There's usually 2 ways. Either you're returning the value if you only need one, or you passing an accumulator, which then records all the solutions. And yeah, you can then access all of these. So if the space is not too big, you can do that. If the space is too big, of course, the function will. Yeah. Yeah. So you can solve it that way. So if you want to have another value. So the largest value would be more interesting, no? I mean, I sometimes find these problems could be more challenging, but it's they're made to be fun, and they're not made to keep you busy for a long time. Even though this one does, it's actually not so easy here.
What's the price after you solve all the problems?
You mean the price when you? So I don't know if there's any price really associated. I haven't done it, so I don't know if there's any. No. I'm not that competitive, but you can kind of see how many people solve these problems. So these are the ones who solved, I think, only the first one, and this is the one who solved both of them. You can actually see that initially there's many more people who solve it. The reason that these get smaller might have 2 reasons. Some people they lose patience, or they find the problems too difficult. But you can see here, for instance, the 24 has only 18,000, 25 is 16, but for this one we need to solve all the previous ones. So this one is an outlier. But 18 has, 24 was difficult, 21 was difficult, and well, 17 was actually not quite so difficult. So this one was actually easier. So people didn't struggle so much with the first one I explained. But this 24 was definitely, I mean, that seems to be, at least from this list, the most difficult one. And sometimes it's really, for some people, it's difficult, for others it's not. I found it not so difficult with these intelligent guesses, because you know something about hardware, and you can use that knowledge. But most people are very software-centric, so they just add 2 numbers in C, and they don't know what happens underneath in the CPU. Or in a system to do this. Once you start writing your own hardware designs, you actually understand that there's actually a logic underneath that does that. And in Germany, I mean, even in Mexico, I think there's courses that teach you how you're building these kind of circuits, even though you would never do it in practice. But it's still good, like what David says, you have propagation delays, which affects the largest speed you can run your circuit. So there's a lot of these things that affect performance measures of circuits, and you it's good to be aware of this. So if there's something you learn from embedded, is to be more aware of these kind of things. So I think we might stop now. Thanks everyone so much for coming, especially Josue for giving the talk. And I hope we can thank you. We can have more socials again in the future. I'm really happy we had so many people today as well. I was afraid that the notice and not having meetup would, but I think we're getting more and more members. And I know this conflicts with another social from Kotlin, so maybe we would have even got more if it wasn't for the clash. And so for the next one, I don't have a topic yet, but I really rely. There's one guy who said he would talk today about security, but he didn't get back to me. So I need to find his email or his WhatsApp to see if he can do that. I really love this Linux talks, and I think there's more we can maybe do in this area as well. And maybe if you're interested, we could also talk more or have more presentation on the hardware side. So not about the high-level software, but like the circuit-based design of stuff. But I'm really open. I have no real preference. I'm just happy if, Sid or someone else likes to give a talk, and then we can keep it. Or David already gave a talk on Pico. Remember, keep it going. Cool. So if anyone wants to join, I don't know if there's a critical mass to have a beer. We can do that. Otherwise, yeah, thank you so much. And thanks to everyone from the YouTube channel. I hope you also enjoyed it. And yeah, feel free to join us in person as well.